Hello everyone, welcome to this new video lecture series on AXI 4. So this is the first introductory lecture, so let's start. So AXI basically stands for Advanced Extensible Bus or Advanced Extensible Interface. Okay, that is a part of AMBA specification that is released by ARM. AMBA basically stands for Advanced Microcontroller Bus Architecture. Okay, so we'll not go too much into details related to the abbreviations and all, rather than we should understand actually what AXI basically means. So AXI is basically an on-chip protocol that simply means that helps in communication between devices existing inside a chip. So suppose this is a chip and we have multiple devices existing inside it. Suppose we have two devices, then these devices can actually interact with a set of rules defined by the AXI. So AXI will be setting the rules of communication between two or more devices between inside a chip. Okay, so one of the devices can be called as a master, the other one can be called as a slave. So okay, there is one more thing, that the terminology uses, AXI uses a master slave terminology for its earlier specifications, while for the new specification it has been changed to a manager and a subordinate without any change. See, so master directly means a manager now in the new specification, and a slave directly meant a subordinate in the new specification. Okay, so what we told is AXI is basically an on-chip protocol through which multiple devices within a chip can interact with each other using the rules of the AXI. So when we have a manager and a subordinate, or a master and a slave, a single master and a single slave, we can have a one-to-one communication between them. We can have a one-to-one direct connection between them. But when it comes to multiple masters and multiple slaves, we cannot have a direct one-to-one communication between them. Along with that, we need some additional information, like in case of a single master, single slave, we know exactly who is going to communicate with whom. That is one master, one slave. But in the case of the multiple masters, suppose there are two masters and three slaves, we don't have a clear idea on which master is going to connect with which slave, right? Which master is going to interact with which slave. So we need additional information that could be, suppose a master ID. You can say it as a master ID and a slave ID. So with this information of master ID and slave ID, we can be able to establish a connection between multiple masters and multiple slaves. Now the device that is being used for making this connection is known as an interconnect. We'll see how this interconnect is going to use this master ID information and the slave ID information. So master ID and slave ID are nothing but the identifiers for the masters and the slave. Okay, so suppose this is our interconnect device represented by IC. These are the two masters, M0 and M1. They connect with an interconnect, and on the other side there are three slaves that connect with the interconnect on the other side, S0, S1 and S2. Now by interaction, what we means, we are actually going to write and read within this slave devices, right? So slave will have its own memory. So memory, I'm representing it just as a block. So 0 to n address, okay? And this could be any number that representing a byte, 1 byte or a 2 byte, okay? So this is the memory for the slaves. Slave memory. Okay. So how this interaction is going to happen is, so whenever a master, suppose say M0, want to interact with a slave named as S1, it will send something known as a logical address. Okay, this logical address will actually comprise of a combination. We are taking a hypothetical example. Suppose the master ID along with the slave ID along with the memory address inside a slave, or you can also call it as physical address. Okay, so now this interconnect knows with this information, this address, with this logical address that, okay, my master, suppose M0, this will be the ID of the master 0 and slave 1 ID. The interconnect came to know that, okay, my master 0 is going to interact with the S1 and it will directly establish the interconnection between these two devices. Now, there could be a possible case wherein two same masters are trying to interact with the same slave. For this case, the interconnect would also have an arbitration logic that defines or that describes the priority between M0 and M1. So, based on that, it will give the access to the particular master. So, we can understand that if we are trying to access the same slave, we cannot have the interconnect cannot give a direct access to both of the masters to one slave because there is a single bus, there is a single address bus, there is a single data bus. That cannot be given access to two different masters. Okay, so what we have to do is we have to serialize the communication. So first either M0 or M1 will interact and then the other one will interact based on the priorities. Okay, so up till now we have seen the interconnections between multi-masters and multi-slaves and also a single master and single slave. So one simple rule of thumb is that we need to remember is in case the number of masters or the number of slaves, whenever their number is greater than 1, we need an interconnect. We should go for an interconnect. Okay, there is no other way of establishing a connection between them. Okay, so far so good. Now we'll move to the basically the signaling that is available inside the AXI interface. So we'll name it AXI signal. So first, the category of the signals that we come across in AXI is the global signals. That includes two signals. One is the A clock and the other one is the A reset in. So A clock is basically the clock used for synchronization between the master and the slave. Okay. How the synchronization is achieved is there is a master, there is a slave. Okay. The clock goes from either it can be from a master or slave or a common clock. Okay. So within the AXI protocol, both of the master and the slave agrees that okay, whosoever will drive the information that will be at always at the POSH of the clock, and also whosoever will sample the information, that is reading the information, that will also be done at the POSH. Okay, so in order to maintain the setup and the hold time, what we need to do is always our information should be stable before the POSH comes, right? In order not to violate the setup and the hold times. Okay, so now the clock, so this is a rule of thumb that always the interaction between the master and the slave will take place only at the passage of the clock and the data should be stable before that. Now there is a second signal, that is the reset one, that is named as the A reset in. This is an active low signal. That is the reset for the whole system that exists for the AXI. So An active low signal simply means that if the signal is actually low, the system is under the reset situation, and it will not allow the master and slave to interact with each other. Okay, and the second thing, if it goes high, the master becomes out of reset. So this is the area where the system goes out of reset. If you see, this is the clock pulse. Uh, this is actually a synchronous deassertion. So there is a rule for the reset signal. First is that the assertion of a reset is asynchronous, and B, the deassertion of the signal, deassertion of the reset signal is actually synchronous. What we mean by this is deassertion of this reset means the system getting out of the reset. When it goes high, it will always happen at the passage of the clock. That is mean by synchronization of the deassertion of reset. But when we say that okay, the reset is asserted, whenever the time at which it gets asserted, immediately the reset happens. So for example, if I extend this clock, okay, and suppose this is the point somewhere here wherein the reset goes low, the system directly comes into reset immediately after this point. Okay, so I hope the meaning of this is very clear. So summarizing once again, so what we told is whenever the deassertion of the reset happens, that is the reset goes from low to high, the system will come out of reset only when the passage of the clock has happened. Okay, because the deassertion of the signal is synchronous. Okay, but when the assertion of the reset happens, this is your reset signal. When the assertion of this reset happens, it get into the reset immediately after the reset is asserted. Okay, hope we understand this point. Okay, now let's jump forward a little. We'll talk about the different channels that we have in AXI. So AXI interaction actually happens with the help of the 5 different channels. Okay, these channels are write address channel, that we will be representing as AW. There is also a write data channel, that we will represent as W channel. We also have a write response channel, representing by B. Then we have the read address channel, represented by AR. And at the last, we have the read data channel. So there exists 5 channels between the master and the slave for an AXI interaction. Suppose this is the master, this is the slave. So the direction of the write address will be like this, from the master to the slave. This is our AW channel. The direction of the write will again be from the master to slave, because there will be data transfer in this channel. Okay. Then there will come a response for this write address and write data. Okay, that will be represented by B. Then there is a read address channel whose address goes from master to slave. So the direction is from master to slave again, and there will be read data coming in from the slave to the master. Okay, so there are 5 channels through which the AXI master and AXI slave interacts with each other. They can be considered as partially independent from each other. Okay. Okay. So these 5 channels have their specific functions. For example, in the write address channel, the master will be transferring the address and the control information from the master to slave. Similarly, for the write data channel, the master will be transferring the information that is needed for writing the data from master to slave. Similarly, the slave will send a response for the data, for the write data that has been sent to it, that it is an okay response or an error. We are trying to do something that is not valid. Okay. Similarly, for the read address, if the master wants data from the slave, what it does is it sends the address in the read address channel, and the slave responds it by giving the read data to it. Okay. So these transactions that are happening, they are done under some handshaking. Okay. So the next topic we are going to take is about the handshaking of the signals. Handshaking existing inside the AXI. Okay. So by what exactly does these channels means is they are exactly the set of signals. By channel we mean that. Okay. So the write address will have certain set of signals. Okay, that will be getting transmitted from the master to slave. Similarly, write data will have certain set of signals. Similarly, write response and read address and so on. Okay. So there exists a handshaking between each of these channels, and that handshaking is being done by with the help of two basic signals that are called as valid and the ready signal. They are represented by AX valid and AX ready. Okay, so X basically can represent any of the channel. So these signals are actually present in each of the channels. Okay. Okay, so how this handshaking happens is this valid signal is indicating that the information that has been written into the bus is actually valid currently. Okay, so suppose they're all others signals except the assertion of the reset are all synchronous signals. Okay, so let's suppose this is a clock. Okay, so this is our clock signal that's called as a clock. Now the master want to drive the data. Master want to write some data into this slave. What it has to do is it has to use the write address channel. First of all, the first step that it has to do is it has to use the write address channel so that it can transfer the information of the address that it wants to write to the slave. Right. So how it is done is first the master has to actually make its AW valid high. Why so? Because that tells the slave that okay, this information is valid now. So the moment this valid signal goes high, now the slave at this point of time, because it is the POSH, considers all of the information that is transmitted into this AW channel as a valid information. Now information once this valid is asserted, all our information becomes valid for the slave part. Now, how the slave responds is maybe the slave is busy for some time, and after a certain set of time, it responds to the master by saying that I am asserting my AW ready. That simply means that I have accepted the information that you have given to me. Okay, so after some point of time, the slave asserts the AW ready signal. Okay, so at this point it happens, suppose. So that is an indication for the master that okay, the slave has now got my information that I wanted to send. That is, I wanted to write at a particular address. Okay, and this has been done. So I can now remove this AW channel information. I can put my valid down. Okay, so this is the area where the information given in the AW channel becomes valid. And it is implicit that we have to uh, have this system deasserted. Means we should not, this system should not be under the reset condition. So definitely we'll consider that the signal was out of reset before this happened. Okay, this is an A reset in signal. One more important point, that when the reset, when the system is reset, none of the valid signals can be asserted. That means none of the valid signals can go high. You cannot claim that your system is under reset and your information is actually valid. So let's see it once again. So what we said is AXI actually holds 5 channels for holding an interaction between master and a slave. Each channel actually represents what? A set of signals. And if the master and slave want to interact, they need a proper handshaking between them, and that handshaking happens with the help of 2 signals, that is called as AX valid and AX ready. So we take an example of the write address channel, because for the write case, the first step that the AXA master has to do is it has to put the information into the write address channel, through which the slave would know the attributes of the transaction, of the upcoming data transaction. Okay, so with this help of the write address channel, what actually the slave tells, sorry, the master tells his slave is, it gives certain information about, like, what is the length of my data, what is the address that I am targeting for write, and many such informations. Okay, so with the help of the write address channel, master gives certain information about the data transactions. Okay, and after that the write data transaction will happen. Okay, leaving it aside, for this write address transaction to happen, the first and foremost condition is the handshaking should happen. So the handshaking signal for the case of write address is AW valid. Okay, okay, so in this case what is happening is the master puts the valid information at this point of time, it gets synchronized at this passage. Okay, so at this passage the master is telling that, okay, I have put some information into my AW bus, and that information is actually valid. So the master is, if you carefully observe this case, the master is waiting for some time for the slave to receive the information. The master is actually waiting for a slave to get ready to receive the information, right? In this case. So it can be a opposite also. That means rather than master waiting for the slave to get ready, there can be a case wherein the slave is already ready and it is waiting for the master to provide the information about the write or the read. Okay, so let's see this case. So this we can consider it as case 1 that we discussed so far. Okay, now let's move to case 2. So suppose this is our clock cycle. Okay, so we are telling that, okay, before this point AW ready was already high. That is a slave signal. Okay, now the AW ready will go low once it receives the information from the master. Okay, suppose this is the point where the master has settled its AW value. Okay, So after this passage, actually, the master asserted its AW valid, and it goes down because it knows that this is the A valid from a master. Now it goes down, and the ready also goes down because the slave has received the information. So in this case, what is happening is the slave was already waiting for a correct information from the master for a valid information. So it asserted here, but gets synchronized at this point of time. And once the master asserts the AW valid, immediately slave sampled that information. Okay, this was the second case. There could be a third case as well, wherein the synchronization for the valid and ID happened at a single clock edge or a single clock cycle, and nobody has to wait for each other. So suppose there's a clock. Okay, so suppose the master asserted its AW valid high here, telling that all of the information that I am providing in the AW channel is valid. Along with that, the AW ready gets asserted from the slave also at this point of time only. So the master driven also this data in this clock edge only. Okay, and the slave is ready to receive this information also in the same clock pulse. So this is the most efficient way because nobody has to wait for each other. Neither master is waiting for the slave to receive the information, and neither slave is waiting for master to provide the information. Right? So here the transaction will happen only in one clock cycle, and this is considered to be the most efficient case for the AXI transaction, for any AXI transaction to happen. Now, a few more points to consider is when the W when the W valid is asserted or an AX valid is asserted, the master or the sender, whosoever is sending the information with the help of the valid, should not change this information until unless the ready is gets asserted. Okay, so there cannot be a change, no change in the AW channel information. You cannot change the information within this period of time until and unless AX ready is asserted. Okay. So similarly, for the previous case where from the time when valid gets asserted until the ready gets asserted, we cannot change the information that is present over the AW channel. Okay. So this is the point where the change cannot happen in AW channel info. Okay. So we've seen the three different cases and we also seen the most efficient case, right? So if suppose your slave was not doing anything productive and it was free, okay, this is your slave that is not doing anything and just sitting idle, okay. So the best efficiency that we can get in terms of the fast data transfer is when we actually assert the AW ready high always whenever it is idle. Okay, so that is the recommended default value for the sleeve AW ready. Okay, so the best transfer will happen when the slave is always asserting AW ready high whenever it is idle, so that if in case anytime the master is sending the information in one clock cycle, it can receive that information within that particular clock only rather than waiting for it. Okay, so the default recommended value from the AXI spec is to have a AW ready high always, whenever the slave is active. So far, we have seen the behavior of the AW valid and ARD signals. Now, what we can do as an exercise for us is we can check for the other signals, the valid and the ready signals from the other channel. That will be W valid and W ready
For a right
channel, right data channel. It will be B valid and B ready signal for the response channel, and similarly the AR valid and R AR ready similarly for the read one. So we can look into these signals and their behavior as given in the AXI spec. AXI spec is an open source material, so we can easily download it from the AMBA website. Okay, along with that, we can go through the introductory chapter that talks about the handshaking in the AXI full spec. That we will take it as an exercise for us. Thank you for joining. Thank you so much.